computing the resources required to give you the precision that you want in the final answer. Okay? So here we want to get the solution to Grover's algorithm by rotating up like that. And now we will utilize this idea of trotterization. But we will only have separate H1 evolutions and H2 evolutions, each of them for some sliver of time delta t. I now need to also compute the number of such evolutions and the size of the time step. And the cost will be in units of this thing here. So every time I run e to the I h2 delta t, no matter what delta t is, I will call this a cost of 1. So I will count the number of queries to the oracle. I will say, oracle, hey, run for delta t, and then give me back my state. And the oracle will charge us a unit cost for doing that operation. Okay? And our question is, how many oracle calls do you need in order to run Grover's algorithm with this simulation business? So let's start with the simplest trotterization, which is up there. And I'll give you the actual formula. What we have is that e to the I h 1 plus h2 t is exactly equal to the e I h t, these can be delta t's if you wish, times e to the I h2 t plus order of delta t, insert deltas there yourself, squared. Okay, and this is true for small delta t's. And so now let us look very carefully at this error term and see what the consequences are. It means that after t divided by delta t steps, so we take the total time of evolution, we break it down into delta t slices. The total amount of error is going to be the number of steps times the error per step, so that we get the error total being t divided by delta t times, say this is now is where I wish I had my deltas. Okay, so let's multiply the number of steps by the amount of error per step over here. And we want this to be no more than a constant, because if the error is growing too rapidly, then it's unbounded. So we want this, for example, to be 1. Let's say it were equal to 1. Then we would find that delta t, canceling 1 delta t, has to be less than or equal to 1 over t. And remember, t is this. So this is 2 divided by pi square root of n. OK, so that's not too bad. But then the number of steps is t divided by square root of t. And this is pi over 2 square root of n divided by this, which is just t squared, which is going to give you n. That's no good. Now the number of steps is n. What is the number of steps supposed to be for Grover's algorithm? Square root of n. So my simulation is now rendered useless. It's no faster than a classical algorithm because I had to trotterize, because the error was adding up too fast. So I have to do something better. So what I do is I pull out Trotter expansion 2. And I try to be a little more clever. It turns out that this is not the only way to approximate. You can do e to the I h1 plus h2 delta t is equal to e to the minus I h1 delta t divided by 2. This is a little weird. I do half of the first Hamiltonian, and then I do the full h2, and then I do the other half. Of course, you should be reading this from right to left, but what I said is still true. I do half, full, half. And if I split like this, the neat thing is that I reduce the error to third order instead of being second order. Okay, that's kind of clever. And the cost is now that I have to do 3 slivers instead of 2 slivers. Does that give you now an algorithm which scales properly? Let's work out the resource requirements in exactly the same way as here, but now for this higher order trotterization. I won't work out the details for you. Let me just give you the result. So delta t with this third order expansion now is such that the cumulative error will be on the order of delta t cubed times the number of steps. The number of steps, again, is square root of n divided by delta t. And therefore, delta t will go as 1 over n to the 1/4. So the number of steps, if you work this out, is square root of n divided by 1 over n to the 1/4, which is n to the 3/4. Ha! We're getting closer. But it's still not quite there yet. Okay, so better yet, better. Still. It turns out what you need is a better trotterization. And in the case of Grover's algorithm, it turns out that a perfect trotterization is known. But if you did not know that, and you were just trotterizing an arbitrary h1 and h2, you would look for much higher order terms, and you would say, well, I do have a delta t to the kth trotterization. You can pull it out of your bag. Such things are known. And then this, you would find, gives you an n steps, which goes as n to the 1/2 times 1 plus 1 over k plus 1. So that asymptotically, as k gets large, you recover this square root. This is capital N here. The square root of n that you expect for Grover's algorithm. Okay, so that is kind of nice. But it's a rather bit of a pain to have to do that. By the way, for those of you in high energy physics, these Trotter expansions are called symplectic integrators. And they're very useful in field theory and other kinds of mathematics where you're trying to integrate over things. These symplectic integrators are also used in numerical recipes for numerical computation in order to make sure that you do not lose, for example, the norm of some system, like the total energy conserved. So they are very useful constructs when you have a conserved system governed by, in particular, Lie algebras. Now, here, we've shown that we had to pay very careful attention to the resources required for the quantum simulation. And that was the third lesson I wanted you to be able to appreciate for quantum simulations.